Now I'll come to the second part of the interaction with photons, and here we have two more effects to discuss. That is the photoelectric effect, pair production, and we'll make a short summary of the effects. Now, if we look at the photoelectric effect, which I want to talk about first, then we have the incident X-ray. Now we're looking at the interaction with an intershell electron, a K-shell or L-shell electron. At this point, the incident X-ray is assumed to have sufficient energy that it can overcome the binding energy of the inner shell electron. This will be ejected and therefore create a vacancy. So the inner shell electron in this process is being removed. What now happens is we have, as we've discussed last time, we have now an excited atom. We have a vacancy here at the K shell. This vacancy, as the atom is now excited, is in a higher energy state. This vacancy is filled by an outer shell electron which falls from this shell to the inner shell. Here in this graphic we have a L shell electron that falls into the K shell. As it falls down, it liberates energy, its binding energy, and therefore it releases a characteristic radiation. We have from the inner shell electron, we also have a photoelectron that's being produced. That's the ejected electron. So what we need is, for this to happen, obviously if the incident photon that comes in here does not have enough energy to overcome the binding energy of the K-shell electron will just say, well, so what? I don't care. I am not moving anywhere and nothing happens. So this process will only happen if the energy of the incident X-ray EI is bigger than the ionizing energy of the electron here for the K-shell, the IK. That's the binding energy of the K-shell electron. So the incident energy should be equals to the energy of the electron afterwards, the photoelectron, plus the binding energy of the electron that it has displaced. So that means, in other words, the binding energy of the electron, this guy here, is equals to the incident photon energy minus the binding energy. So to summarize, we have a vacancy in the K shell. This vacancy is filled with a electron from the outer shell. It could be the L shell, like it is shown here in the graphic. Here, it could be the M shell. If it is the L shell, then this will create a vacancy in the L shell, will be filled by an electron, for example, from the M shell, etc., etc. So you could have a cascade of characteristic X-ray quanta that are being emitted in this process. We have also another process that we've discussed last time is the process of producing Auger electrons. This is in principle possible, but this is not so frequent in biological tissues where we have soft tissues with a low Z. So the photoelectric effect is abruptly increases when the energy is just above the ionizing energy of, or the binding energy of the electron, and this gives rise to so-called absorption edges. The absorption edge increases with Z. It is actually very low for hydrogen, carbon, nitrogen, and oxygen, which are primary compounds of tissue. The absorption edge energy is a reflection of the binding energy of the inner shell electrons, and therefore, as we've discussed last time, it makes perfectly sense from Coulomb's law that this is proportional to the number of protons, which is therefore proportional to the atomic number Z. So here's a display of the mass attenuation coefficient as a function of X-ray energy. We have two examples here, barium and iodine with high Z, and we can see here the mass attenuation coefficient decreases rapidly and then suddenly increases. That is where suddenly the photon energy surpasses the K-shell binding energy of either barium or iodine. Iodine here and barium here. For tissue, we do not see those K-shell edges because the binding energies, the K-shell binding energies, are well below 10 kilo electron volt. So why do we have these edges increase and then we have the effect increase? Well, basically the way to look at it is, if the energy suddenly is sufficient to ionize inner shell electrons, there are more electrons that the photon can interact with in the tissue, in the material, and so if there are more electrons that are now potential candidates for interaction, then the attenuation coefficient discretely increases. Interestingly, the photoelectric effect is what Albert Einstein received the Nobel Prize for. It was not the Einstein-Stokes relationship for diffusion, and it wasn't special relativity, it was the photoelectric effect that he was awarded the Nobel Prize for in 1921. So, now the fourth effect that I want to discuss for completeness sake is pair production. Pair production happens when the photon energy is bigger than twice the rest energy of the electron. In case that photon interacts with the electric field of the nucleus, then it can disintegrate and produce an electron-positron pair. So it produces an electron and its antimatter equivalent of a positron. The kinetic energy of the produced particles, E, is equals to the photon energy minus the rest energy of the two of the electron and positron combined. They have the same mass, so it's 2 times the mass of the electron. Here's an illustration in a Wilson cloud chamber. So we have an incident photon. It's in a magnetic field that produces a positron here and a electron on this side. Now this effect is not important in bioimaging. Why is this so? Well, we have to look at the photon energies that are being used in bioimaging. And as you will see, the energies that are being used in X-ray imaging are well below the 1 mega electron volt required for pair production. So the pair production effect is not important in tissue. So here I want to summarize the interactions. We'll start with coherent scattering, that is Rayleigh scattering. We have the photon, the way the light is being deflected, but it retains the same wavelength. Therefore, in this animation, the color does not change. Then we have the Compton effect, which happens on the outer shell. It's a electron is being liberated, it's ionizing, and the photon changes its wavelength, as you can see with the change in color. Then we have the effect of the photoelectric effect. In this case, the photon is being absorbed by the inner shell electron. Inner shell, it is completely absorbed. There is the inner shell electron is being liberated, and then we have the cascading event from an outer shell electron filling the vacancy in the inner shell, and thereby releasing the characteristic X-ray for this particular atom. And finally, pair production, the X-ray the photon interacts with the electric field in the nucleus, and it produces a positron-electron pair as a result. So to summarize, if we look now here in the tissue, we have the linear attenuation coefficient mu as a function of the photon energy here on the x-axis. Notice that both scales are logarithmic. And if we look at these two, at this graph here, this is the total absorption, and then these are the different contributions. Rayleigh falls off fast. We have the photoelectric effect, which falls off also very fast. Compton effect has a relatively smooth dependence, and here pair production only starts to happen here at above a mega electron volt. Now, what are the typical energies that we are dealing with for CT and SPECT, which we will discuss in the next 2 weeks? We are in the range of 30 kiloelectron volt to around 150 kiloelectron volt. So this is roughly the range for CT and SPECT. And for positron emission tomography, which happens at 511 kiloelectron volt, we are here at this range. We're far from pair production, and we are at a point where Rayleigh scattering is really not much of a contributor. So in reality, to understand the absorption in tissue, we really need to just concentrate on the photoelectric effect and on the Compton effect.